Hello, it's David. Sorry, I've been quiet for the last few weeks. I've been working on the PiStormST previous video, and it's slow going. To be honest, there's not a lot of progress to report other than using a bit of a cheaty technique with writing data and just carrying it on as if it has magically worked, even though sometimes it might fail with a bus error. I've managed to speed up writes to be 100% of their normal speed, writes to RAM, but reads unfortunately are still only running at half speed, and I think it's because really the Pi emulator is not quite fast enough to have the next read ready in time, and the way memory works on the ST is that you have a certain amount of slices for the CPU and an opposite number of slices for the video display, and if you miss your turn, like if you miss your slot at the airport and have to sit and wait on the tarmac, then well, you have to wait until your next go, and so everything slows down by half, and that's what we're seeing at the moment. So that's now a software problem, very boring, not much to show you, although follow my my Twitter feed if you'd like more information on that. Why am I showing you this radio? Well, it's summer here in the UK, and one, that means sitting in the shed and working is pretty hard, but two, it means there's a lot of cricket on. Now, I love cricket. I'm injured at the moment, so I can't play cricket, but I do like watching cricket, and when I was a youngster, the trick was that you put the telly on to watch the test match, and you turn the radio on to listen to test match special, because the radio commentary is always better. Now, unfortunately, with the advent of digital broadcasting, this is a DAB radio, and digital video broadcasting, plus satellite delays, the two no longer synchronize. So if I turn on my handy transistor radio here, and I put on the TV, I will hear of a wicket probably about 5 or even more seconds before I get to see it on the TV. Now that's fine actually if it's on in the background. I'm sort of listening and you can hear something happen and turn around and watch it in time, and actually that's really handy with a game like cricket where you might be doing the washing up instead of sitting there and watching it religiously at all times. But say I'm watching a football game and I'd like to do the same thing. The commentary's on the radio, the game's on the TV, but then it's very boring to hear the goal and then maybe 15 seconds later you get to see it on the screen. So for a long time I've thought what I would quite like to do is to build myself a little box that just does an audio delay. It samples the output from my radio here, it stores it in memory, and it plays it back a configurable amount of time later, so I can wind the delay up or down depending on which channel I'm watching, which sport I'm watching, and whatever other factors are involved. DAB radio has a delay as well, so it's not a completely linear, that's not the right word, it's not a completely identical experience with each particular thing that you're watching. Sometimes there's actually a lag that grows. So that's what I'm going to look at today. It's going to be a little project where we build an audio delay device that can be configurable to a certain amount, and just using fairly simple breadboardable parts. Okay, so what I plan to use for this is Arduino Nano as the base unit, the microcontroller. This means that I can do most of the work on in software, and this is just a nice simple cheap microcontroller which we'll use as the basis. I've got this 2-line LCD screen which has an I2C board on the back, which we'll use for display, although I do have a few of these Gotek 8-segment displays left over. I think these are very simple. I think these just use like a shift register or something. There is an Arduino library to drive them, I think, but like if we're just showing seconds or something, we could use that. And I've got some rotary controllers. This one's in a module format, which I will probably use as the main form of input. And how I was thinking to approach this was very simply, we'll start off with the Nano there, and on first approximations we'll use one of the analog, say A0, one of the analog pins as the input from our audio source. Now obviously the Nano is 5 volts supply, ground. I mean internally it's 3.3 volts, but I believe this is referenced up to 5, and we would need to shift any audio up to the 5 volt level if we're going to sample it, because otherwise if we've got AC coming in here and this goes negative, well, we're just not going to get any input. We're going to get our, if there's our sound wave, we're just going to get the top half of it. That's going to sound pretty terrible. So we'll come up with some circuitry up here to do that in a minute. The hardest bit, I think, is going to be getting the output. So if this is our speaker output over here, then what I initially thought we might do is to use a simple resistor ladder, and to go into obviously this is also going to be between 5 volts and ground. Use an op amp over here to boost it up, and the simple resistor ladder would connect to digital output pins on the maybe D0 on the Nano, and by arranging these so that they go up as multiples of 2, we can basically drive ourselves, well in this case this would be a 4-bit output, so say that's 1K, that'd be 2K, 3K, okay, I know that's not a real value, oh sorry, not 3K at all, what am I talking about? That'd be 4K, and that would be 8K, and then by simply outputting a binary number from 0 to F over here, we will get a variable voltage out over here from 0 to 5 volts. Anyway, so that was my initial thought, and that would work, and it's basically the same technique that I've adopted for my 12-bit true color ST graphics card. And you can see down here there are 1, 2, 3 rows of 4 resistors, and this is exactly what this is doing. That's a 4-bit output on the red, 4-bit on the green, and 4-bit on the blue to get us our 12 bits. Works fine. But if I'm going to breadboard this up, and if I want to do this properly with a decent level of resolution, I'm going to have 8 minimum, 8 resistors, and I've got to make sure they double, or mostly double, all the way down, and it's just going to get messy because it's probably going to end up with needing to have 2 resistors in series, or 2 in parallel, or more even, to try and get that factor of 2, or nearly 2, consistent all the way down. So for the princely sum of £1.30, I thought I would instead invest in one of these. So this is an MCP4901. This is an 8-bit digital to analog converter with an SPI interface. So this comes in a variety of layouts. However, I'm interested in the PDIP. So it's plastic dual inline package. And here we are with a standard SPI pinout. We've got our source and ground voltage. We've got our chip select. We've got an SPI clock, we've got an SPI data in, we've got a voltage reference which we can tie to ground, I think. We've got a that's just a latch enable switch, and we've got our voltage out. So fortunately the Arduino has a very easy to use SPI library. So this one chip will save us having to do all of these different resistors, and also it'll save us having to do the amplifier on the end. We'll probably still have the amplifier on the end, or we could just connect to line out. To be honest, I think line voltage is generally between plus and minus 1 volt. So we don't want to be going 0 to 5. So what we would actually have to do is to scale this a little bit so that we end up, say, roughly from 2 volts to ground, which we'll need to have some kind of resistor divider in there just to lower that down, or this final op-amp stage needs to have about a divided by 2.5 gain. So if we employ our 4901 DAC here, here's our Arduino, there's our input coming from A0. That little circuit up there is still to be decided. What we want to do with this is to pass through a chip select line, a master out slave in, or as it calls it in the data sheet here, it calls it the SDI line. And that's a clock, SCL. So on the Nano, the clock is pin D13, I believe. That's the same pin as used by the LED, I think. So we won't be able to use the onboard LED for that. The master out slave in is, I believe, a D11. I'll link the image in so you can see why I'm referring to these pins. And the clock, the chip select line can be any pin, or any pin that I can drive digitally. So we'll choose that depending on our breadboard layout. VREF, if we look back at the datasheet again, so VREF is the voltage reference input for the device. This reference on this pin is utilised to set the reference voltage on the string DAC. The input voltage can range from VSS to VDD, and I'm supplying VDD. So this can be tied to VDT. Okay, so that will just go up also to the 5 volts. LDAC, latch DAC output. So the latch DAC synchronization pin is used to transfer the input latch register to the DAC register. So basically we can load it but then wait to assert it if we wanted to make sure we had very nice even slices, say. I think for this first pass we'll just let it update as we go. So when this pin is low, VA is updated, so we can just tie that, there we go, we can just tie that to ground, and basically that will update whenever the chip select line gets deasserted. So then down here we've got our V out, which is going to be the output to our next stage. I think for the purposes of testing, all we need to really do is to put that through a decoupling capacitor. So this is going to be going from, like I said, 5 down to 0 volts. We should probably introduce a scaling factor here. So what I would suggest is we'll put a resistor down to ground here, and we'll make that variable for now. And we'll send that into a capacitor, big old electrolytic with the positive at this end, and we will run that through some kind of nominal, let's call it a 33R. We could do 100, 33, 75, something like that resistor, and that will be our output. So what are we going to do for the input? Well, if we have our genuine line in over here, and bear in mind, same thing is going to apply, that our line in is probably going to be -1 to 1 volts. Well, we're going to need to shift it initially up to a level that stays completely positive. So whenever you hear that, you know full well there's going to be a capacitor coming in here, probably another big old electrolytic with the positive side over here, because this is going to be going from 0 to 5, whereas this is 1 to -1. This is always going to be higher than this. And we're going to have to bias this component somehow. So well, the most obvious way to do that is to set a reference which is half of our 5-volt supply. So what we do is a little resistor divider here. We'll make these something relatively large. Let's call it 10K. Could be 4.7, it doesn't really matter. So what we know then is that here at this stage we're going to get about 2.5 volts, and we'll use that to bias this input. Now what we can't do is drive that, well I suppose we could because this is 10K each way, but if we drive that directly we're just going to get 2.5 volts on here. So we want to drive it through a fairly reasonable size resistor. Anyway, we probably actually want it to be a higher resistor than this because we don't want this to be affecting this at all. So I'd probably put it through something like 47K. So let's insert our resistor here. We'll go for 47K, and that's going to bias the input to A0. So now A0 should be plus and minus. No, that's the wrong terminology. It's not plus and minus. It's a waveform centered around 2.5 volts. And because this is probably -1 to +1, this is going to end up being 1.5 to 3.5 volts, which is fine. Our resolution here on A0 is not going to be brilliant. In fact, the internal reference for the Nano I think is pretty crap, but there is the opportunity to supply an external analog reference there. So that might be something we come back to later. But for the purposes of testing and getting a prototype up, I think that's absolutely fine. So we should get something with a limited resolution. I don't know what this is. I don't think this is genuinely 16-bit on the input. I'm not sure. So let's say we get half that. So if we were to get effectively 8-bit resolution, well, that's fine. We've got an 8-bit output DAC. So I think that should work fine. So what I suggest is we breadboard this up, and then we look at testing it. I think first things first, can we generate ourselves a tone, and then can we actually sample some input and play some output? We're talking about voice. We don't need it to be 44 kilohertz 16-bit. If we get 8 kilohertz 8-bit, or effectively, if we've only got a limited subset here, even if it's 4-bit, it'll be enough to demonstrate the proof of concept, and we can always look at introducing better quality audio components down the road. This is what I've come up with then initially. So standard breadboard, negative negative, positive to positive. We'll charge, or we'll power the entire thing from the 5 volts supply going into the Arduino, the Nano. Let's just bring in the circuit board here, the circuit diagram here, so I can show you what's what. So starting at the input, that will come in on this 3.5mm jack. This goes into this line here, which is coupled via this 47 microfarad electrolytic to a 0 input here. That also has a 47k resistor going into this resistor divider here. Oh, it's just going into positive on both sides. That's a mistake on my part. That should be going into the going into ground on that side. So that's going. These are 10Ks. So positive in at that end, negative in at that end, bridge in the middle. So we know we've got 2.5 volts at that point there, which is being coupled to A0 by this resistor, and the capacitor going off to our input. The second to our input is going to ground, as per the diagram. So from the Nano to the DAC, we've got these 3 lines. So I have connected D13 there with that grey line. That's going into pin 1, 2, 3, 4, 5, 6. No, sorry, one from that side. What am I talking about? 1, 2, 3, pin 3, which is the clock line. D13 into the clock line. I've got this orange one coming from D11 down here into pin 2. So pin 2 is the chip select, and so we can now fill in. Oh no, D11 is. I've made a mistake there. D11 is going into. Sorry, that's pin 4. So that's SDI. So yeah, D11 into data in. So master out, slave in, the MOSI pin, and then we've got D7 down here. That's going round into pin 2, which is our chip select. So that's what we're going to update that with. So that's going to be D7 up on the diagram. The other pins on our DAC, we've got obviously there's VSS. That's ground. Sorry, that's that one there. We've got VREF, which is going to 5 volts, and we've got LDAC, which is going to ground. So that matches what we've asked for here. And obviously the VDD is going to the +5. That's voltage drain. I've got a 100 nanofarad capacitor across the power lines there, which is the recommendation in the datasheet. Also recommends a larger bit of bulk capacitance, but I'm not putting that on here just for this initial test. So with everything configured like this, we ought to get our signal out of pin 8, which we can touch the oscilloscope via with the ground line. Oops, so my suggestion is to connect up the oscilloscope probe like so. So we're going between ground and that output pin, and what we should see is whatever we have commanded the DAC to produce between 0 and 5 volts. So let's go away and write ourselves a test sketch for the Nano here, and we'll see whether we can get output that we expect on the probe. Let me give you some news from this channel's sponsor, PCBWay. A year ago, PCBWay moved into a new factory, and now they've had time to get their feet under the table, they're able to offer some substantial price reductions. There's up to 20% off 4 and 6 layer boards, bulk order prices are down, and 5x5mm track width and 1/4mm minimum hole size designs will also see huge discounts. The event started on the 5th of August 2022, and you need do nothing special to obtain it. Why not log in now and see if your design, manufactured to PCBWay's normal quality specs, is much cheaper than you thought all of a sudden. And if you're there, maybe take a look at their CNC machining, sheet metal fabrication, 3D printing, and injection moulding services whilst you're at it. See the links at the bottom of this video for more information. Okay, so here we are in the Arduino IDE. This is a very simple starting point. I like to do my development in a slimy style, slice by slice. So just getting the basics out of the way. First of all, I'm going to include the SPI header library. This is the just setting it up. So SPI mode 0 there, that's the default, but I think when I look at the data sheet here, it tells me that it supports mode 0, 0 or 1, 1, so I think mode 0 is fine. Most significant byte first. So yeah, I believe that's also how it works in the datasheet, or how it's defined. I'm going to set pin 7, so that's D7, which was our chip select pin. I'm going to set that to an output, and I'm going to write that high, so that's the chip is deselected. I'm going to start a bit of serial port for debugging, and that's all I'm doing at the moment with the SPI. So that should basically disable any commands going into my SPI DAC chip. Then in the loop, I've got a global variable called SND for sound, and I am setting it to this particular construction. So what's going on here? So this is me basically just doing an initial tone generation to test that I can get some output from this DAC. Now the idea is I'm just going to oscillate. I'm not reading any input at all at the moment. I'm just going to oscillate this this output pin so that we can measure it on the oscilloscope. So what we've got here is, let's break it into chunks. So first of all, there's a sine function. I can write it out again. So first of all, we're doing a sine of a parameter. Now in this case, the parameter is micros, which is a built-in function, which is the number of microseconds since the Arduino was booted. I'm going to divide that by a large number to slow things down, and I need to cast, this is all in floats, so I need to cast, maybe in doubles actually, but I'm going to cast it to float type. So I'm going to cast micros to float and then divide it by a floating point number and pass that into the sine function here. Why have I chosen 36,000? It's just a nice big number that I should be able to see output relatively straightforwardly if we do some quick maths on that. So that's it's basically microseconds divided by 36,000. So in effect 36,000 microseconds. So that's 36 milliseconds. So 1 divided by 36 is 0.02, and then times 1,000 because that was milliseconds. So 27.7 by my reckoning, 27.7 hertz. So this is a 30 hertz roughly signal, which is viewable, and it's actually in the audio range. It's very deep bass. It's below bottom G, which is around 47, I think. So that's that should be audible. Not that I plan to play it back at the moment, but it should be measurable as well. So that's what this is here. Now that will obviously create a number going from -1 to 1. So I want to shift this to be entirely positive. So again, 1.0 plus sine. And that will create a number from 0 to 2. Now I have got an 8-bit DAC here. So 8 bits means that you can go from 0 to 255. I want to go, I just realised I've done this as a 4-bit DAC. So I want to go from 0 to 255. However, I'm going from 0 to 2, so really I need to multiply this by 128. So 128.0 times 1 plus all of that, and that should go from 0 to 2, 5, well technically 256, but 255 point a high number. So maybe I'm going to multiply by 127. Close enough for government work. So that is how I get my S&D variable. Let's change that to 128. I had in the back of my mind that this was 0 to F, but it's not. It's 0 to FF for 8-bit DAC. So before we do anything with the SPI interface, why don't we print that out? So we can make sure that's doing what we expect. Save that. Let's set up my. Hold on. Let me just plug in the Arduino. Okay, and now we can choose. There we go. Let's pick it up. Choose our port for the Arduino, and let's upload that image. There we go. Writing AVRDU done. Thank you. There we go. So I've got the green transmit light on over here, so let's try opening up the serial monitor. And we've got gibberish. Ah, no, there we go. Perfect, right, so that's too fast to read, so we'll turn off the auto scroll. And what we should see is numbers slowly going from, around in the 0 region here, up. It should get us about 255.99, there we go. And back down to 0, and it should be doing that roughly 30 times a second if my calculations are right. So that looks good. And obviously, well, we could cast that to an integer, and then we should actually get the numbers that we're expecting. There we go. So when I say expecting, ones that we can actually pass through to the digital to analog converter. There we go, down to 0. And up to 255. Perfect. So, right, the next thing to do is we need to write our SPI commands. So it's time to take a look at our datasheet again and to see how we are going to actually issue these SPI commands. So the write command is initiated by driving the chip select pin low, followed by clocking the 4 configuration bits and the 12 data bits into the SDI pin on the rising edge of SCK. Right, so the library will do that for us. We've tied LDAC down, so all we need to know are the commands. So all write devices are 16-bit words. Okay, no problem. Anything past that will be okay, fine. So let's have a look. What have we got? Here we go. Register the write command register for the 12-bit, the 8-bit. Here we go. So the 4901. So 1, 2, 3, 4. So the first 4 are the commands. So we start with a 0. Bit 15 is a 0. Write to DAC. Oh, and 1 is ignore. So we write to DAC. Then the buffer control. Well, we buffered or unbuffered? Not sure. Let's go buffered. Then we've got bit 13 is the gain selection bit. So let's have a look. So 1 times V out equals VREF times D divided by 4096. I'm not sure. Let's go with 1 times for now and see what we get. D divided by 4096. I was planning to pass up to 255, so it could very well be that we need to run to 4096 actually. Okay, right, so if I pass 4096, then we get VREF, which is set to the input voltage. And if I pass, okay, and with that one, pass 2048. Okay, so it's a scalar. We'll go for 1 times, and yeah, I think I'll need to. I think I need to rescale to 496 rather than 256. That's fine. Shutdown control bit, active operation via is available. Shut down the device. Not available. So we'll set that obviously to active. Bit 11 to 10. 11 to 0, those are our data bits, and obviously we only are going to send 8 of those, so we would shift our data along a bit. But this is interesting. Well, for starters, I'm just going to use my 255, I think, but it looks like I should go up to 4096. And also, it looks like VREF, we could actually, I've designed in my circuit diagram here that we have a variable resistor to moderate the output from 5 to 0 volts down to a lower value. But I think it looks here like I could just feed in a lower VREF, and this would actually scale for me. So if I were to feed in 2 volts as the VREF, then this would actually scale it for me. So it might be a modification to the circuit diagram coming up. Okay, so I've just copied a summary of that information into the comments here for my reference. I don't need that serial output now, so we'll get rid of that. And what I'm actually going to do now is perform the write to the SPI bus. So the first thing we have to do is to drive the chip select pin low. So that's a digital write to pin, what do we have? Was it 7? Yeah, pin 7. So we'll set that low, then we'll perform our business, and we would set it back to high again. So the way we've got it configured at the moment with the LDAC pin tied to ground is that when the DAC will be driven, the DAC is driven when that pin goes high. Now the actual transfer is carried out by the SPI library, so we use the SPI transfer function, but because this is a 16-bit word from the datasheet there, we use SPI transfer 16, and we'll define a variable called transfer, which will contain our information. Right, we haven't defined that yet, so that's going to be a 16-bit int. I'll pop that up here, and we're going to start off by setting that, starts off with our command. Okay, so referring to our command information up here, that's going to be, and we'll do it in binary, it's going to be 0 for write, then 1 for buffered, gain output is going to be 1, and it's not shut down, so active is going to be 1. They need to be shifted to the left to make them the topmost bits of the 16, so that's going to be 12 bits shifted to the left. Now with that in place, we'll need to send our value. So our value is going to be that SND figure. So we cast it to an int, except that's going to end up in the bottom 8 bits, whereas we need it to be in bits 11 to 4. So much like we shifted 12 there, what we'll have to do is just move this left by 4. And so there we go. That should be our transfer variable. Remember that the bottom 4 bits do nothing, as we only have an 8-bit DAC. So I think we can write this to the Arduino and get our oscilloscope out. Okay, so here we are. Forgive the background noise. The oscilloscope makes a bit of a buzz. Now let's get this hooked up. So I've flashed this already. But at the moment, if it's working, all it's doing is just driving this this wire with nothing attached to it. So we should be able to connect up our earth or ground lead over here and attach to this. I can see that the LED in there, I don't know if you can just make that out, the D13 LED is partially on. It's probably not coming across in the video. So given that that is our clock line, that's to be expected, so it should be about half brightness. Right, and let's get that attached, and there we go. Look at that. That's a lovely looking sine wave. Okay, our voltage average is 2.56 volts. There's the ground level. It's going all the way up to, well, near as damn it 5 volts. So maybe I misunderstood that 4096 business. As this is, I haven't changed this. It's still it's still feeding a 0 to 255. Oh, of course, the 4096 is after I have shifted it left 4 places. I could have multiplied it by 4096 in the code and not done the shift left. Okay, same thing. Right, so yes, we've got our 8 bits. There we go. It's looking really nice. That makes a lot more sense to me now. So brilliant, actually. What is the what's the frequency we're getting there? How close was I in my estimate? 4 Hertz. So not very close at all. My of course, there's a factor of 6 in there because 2 pi, factor of 6. So what did I come up with? I came up with 27.7 Hertz. Divide that by 6.2-ish, and you get 4.46. 4.4. Yep. Okay. I missed my factor of 2 pi. Goodness me, wouldn't believe I was a physicist, would you? Right. So there we go. Output looks perfect. Really, really happy with that. So, well, the next thing to consider is, well, can we get it to follow something that we put on the input? Okay, so back to our Arduino setup. So the first thing we want to do is to declare another pin mode, but this is going to be for our input. So pin mode, and we used pin A0 in our network diagram, and that's going to be an input. That's obviously meant to be an analog input. So having duly declared that as such, we now need to read it down in our loop. So at the top of our loop, we're going to do a simple sound equals analogRead A0. Now that's going to go from 0 to 1023, I think. And if we want to get it down, so we don't need this one, this calculator one anymore. So if we want to get it down to 0 to 255, we're going to have to divide that by 4. So we'll just put a divide by 4 in there. This is all integer maths, so that should be legitimate. Why don't we print that out just to make sure that our range is correct? So I don't have anything connected at the moment, but if I were to program that, what do we get on our output? Okay, we're getting 127. There's nothing on there. That's halfway. Our circuit, which is designed to drive at 2.5 volts, should generate about 127, 128. So, well, that's promising. I'm tempted to connect up some audio input. Okay, so here's a my iPad connected up to our audio in, and it's my last video, me clattering away about a desoldering station. And well, here we go. Look, you can see we've got some variation in our levels. We're going not very much deviation at the moment, but that's to be expected. This is probably earphone input, and we are which is maybe plus or minus a volt at best, and of course we've got a 5 volt detection range here, so we're actually really not using the full extent of our sampling. So that's something that we can improve down the line, but really I'm interested in the delay at the moment. So let's just hook up the oscilloscope and see how that looks. Let's power that on and see whether we get what looks like an audio waveform this time. Well, we're not getting the full 5 volts deflection anymore, clearly, because of that very small amount of wiggle that's going on. But look, there we go. There are actually patterns. Turn off measure. Just speed up the refresh a bit. There we go. Look, that could potentially be audio. Let me Let me just pause the video here. And it just dies away to hum. Starting again. There we go. So it looks like we've got something, albeit obviously at a much, much smaller level than we're expecting because of this sampling from 0 to 5 and this probably producing, in effect, 0 to 1 volt, maybe even less than that. Okay, so what I've done is taken the output across to here. That's going through our, that's a 47 microfarad cap. That's then coming back through this. This is a 100 ohm resistor. Just happen to have that laying around. That seems perfectly fine to me. 100 ohm resistor into the output of our speaker terminal, which is then going back to ground, and that should that capacitor should decouple that and allow us to run it at that ground potential. And what I have here is input to a little Bluetooth speaker, which I will now connect up. Okay, I don't know if you can hear that. There's some clicking going on. Doesn't sound all that brilliant. Let's see what it sounds like when we start the video up. Move that speaker over there, and we will press play. Well, that's me, but the quality's terrible. Now, the most obvious thing that's going on there is that I'm printing each one of these values out to serial, which is not conducive to keeping things real time. So I'm going to modify the program quickly off camera here to disable that serial output. And there we go. We'll see what it sounds like now.
Is that they apply a constant flow of air as you heat the pin.
Well, that's still not great,
Using the path,
but that is
this
much more like me.
One, you have to heat with the soldering iron that's on the pin.
So, we've proved we can sample from the input, albeit improperly. We can produce the output, albeit with very little in the way of control. In fact, I haven't even fitted the variable resistor here yet. And we can get discernible sound out. But what about the primary task of delaying the audio? Let me unplug that because that's hurting my ears. What about the primary task then here of delaying the audio? Well, what can we do about that? And that's what I'm going to concentrate on first. So we've got our audio coming in, it's going straight into the Arduino, it's getting sampled by the really low quality internal sampler, and we're getting very low resolution there because I haven't scaled this to 4.5 volts, nor have I added an external analog voltage reference, both of which will give us much bigger, will give us much better bandwidth. And so the output sounds crummy and it's ticky, 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 ticky because, well, frankly, we're just going around in that loop. We're spinning in that loop. We're not using interrupts. We're not using the direct port access. We're just using the Arduino libraries analogRead and digital write, which is, you know, not great quality. Fine, purely proof of concept. We're throwing the output out and we can hear my voice. What we want to do is to store as many of those samples as we can and play them back a little while later. Now, the Arduino itself does not have much internal memory. I believe it only has about 4 kilobytes of, maybe even less. It will show me in the output. I'll check in a minute. Say it has 2 kilobytes of internal memory. Well, we can store then 2,000-ish samples. Obviously, my program also needs to fit in there. So let's try that and see if we can notice a significant shift in the audio. In fact, if I just do a verify, there we go, here we are. Sketch uses 2046 bytes, 6% of the program storage space. The maximum is 32 bytes, but that's the flash memory storage space. The global variables use 187 bytes, 9% of dynamic memory, leaving 1861 bytes for local variables. The maximum is 2048. So here's what I'm thinking. We can use about 1800 bytes to store these 8-bit values. That means we can have 1800 values. Now, obviously, we're still not using these properly at the moment, but as in, scaling these properly. But okay, 1800. So I don't know what we're getting. Maybe we're getting about 5 kilohertz sampling rate. We should be able to get a fifth of a second delay. So let's set that up. So we're going to explicitly declare a unsigned integer 8 type, which I'm going to call my what should I call it? My data store, my memory. Let's call it memory, and that's going to be an array of, let's say, counter values. Now I'm going to define the counter here so we can change it. So counter, well, that was about 1800. Let's see if we can fit 1800 in, because I'm actually now adding more processing logic, obviously. So that's going to be 1800 there. Now what we're going to need to do is also define, if we're going to have this as a ring buffer, we need to define where we're writing to and where we're reading from. So we're also going to need 2 additional variables, which I'm going to call, say, counter in, and we'll initialize that to 0, and counter out, which is where we're going to read from, which I can also initialize to 0. Well, that probably won't do much because they're the same, but we'll come back to that. So then what we're going to do is we're going to read our sound variable here, and we're going to store that in our memory at our counter in location. So mem counter in equals, and of course this will be converted down to an unsigned int 8, which is fine, snd. So then what are we going to play down here? Well, we're going to play our counter out. So mem counter out. And in this case, because counter in is equal to counter out, that's going to be absolutely the same. So we'll need to increase our counter in at the end of the loop, and the counter out at the end of the loop, and round it will go. And we can compile that and make sure that that fits on it. Made a mistake. I've forgotten to terminate that. Oh, and I've terminated the wrong one. There we go. Still not happy. Oh, int counter in. There we go. That's uploaded to the board. And if I were to plug that in and run that again, I should get the same output as before. Well, haha, yes. Did you see my deliberate error there? I'm not reinitializing the counter. They're not looping around, so it'll just go zooming past that that first upper bound, and I'll get nothing out. So I need to check that. If counter in is equal or greater, let's think. We want to be equal to counter. Then counter in is equal to 0. If counter out, nearly made another mistake, is equal to counter, then counter out is equal to 0. So that should reinitialize them, and they should now wrap around. So let's try that little experiment again, and I'll reconnect my speaker.
And this is presumably the pistol.
And there we go. I can hear myself talking. So the next obvious thing is, well, what about the delay? That's the 0 delay there. So 1800 fits. Let's just do that verify again, and we'll see that 57 bytes. So I can't really squeeze much more in. So 1800 is going to be about my limit with the internal memory on the Arduino. But if I start my counter in at, let's say, the furthest distance from my counter out, so that would be 0, and my counter out should be 1. I will basically be chasing the last output one with my new input, if that makes sense. So we're going the full ring. That should give me the maximum possible delay with this Arduino. So let's give that a quick try. So what if we were to feed in a metronome signal here? Perhaps, obviously there's no visual indication, but perhaps we could measure this on the oscilloscope. Okay, so our metronome's going in the background there, and first thing I'm going to do is I'm going to try and probe actually the chip select line. That'll just give me an idea about what sort of frequency we're sampling at. So there it is. This has popped up with an 8.3 kilohertz figure. Let's there we go. Okay, that's relatively regular. Remember, we're not using any interrupts or anything here. So that's saying 8.3. We'll measure time, frequency. There we go. Yeah, 8.33 kilohertz. So okay, that's not too bad. 8 kilohertz sampling, given we're not doing interrupts, is pretty reasonable. But that does mean, of course, that at only 1800 samples, we're going to actually be saving even less, or shifting even less time than I had hoped. So all right, we'll go back to our input now. Okay, so we're probing A0, and I've actually increased the metronome to its maximum, which is 218 beats per minute, and we can see the pulses on here. There's an awful lot of noise as well, but we can now see the pulses here on channel 1. So if I connect up channel 2, and we'll do the same thing, except this time on the output stage. Let's see what we get. Well, there we have it. Input, output, input, output. They are slightly different. Well, I've got them set to different vertical scales. There we go. We are seeing a positive delay. Now, if I remove that counter offset again, I'll set them both to, so the counter in and the counter out to be 0, and we'll reflash our Arduino. There we go, perfectly in line. So as I increase that, let's say I'll make that 100 steps this time. The counter in is 100, the counter out is 0, so the counter out lags the counter in by 100 cycles. There we go, we get a very small offset, and that can go all the way up to, well, effectively 1799, which should bring us back to that maximum delay that we could achieve with this setup. So let's freeze that there and do a measurement. We'll go, actually we can go from the, we'll just do it with the cursor. Cursor, come on, turn on, there we go. So from there to there, just turn that off, that's very annoying. Right, there we go. So the delta time is 218 milliseconds, about a fifth of a second, as we just rule of thumbed it earlier on. So okay, great. We have proved that we can delay the audio with a simple Arduino Nano, and okay, a slightly less simple but a really cheap 8-bit ADC. There's quite a lot of work we can do to improve this. The audio quality is terrible. The level shifting is abysmal. The actual bandwidth in use on the input side is negligible, and to be brutally honest, there's a lot of background hiss and tick. But that's for part 2. Thanks for watching. See you next time.